Hi Rockridge, it's Mrs. Berger again, talking about Algebra 2, Unit 2, End Behaviors of Graphs and Graphical Composition and Inverses. So today is day 12, second day of Unit 1. So the first thing we'll talk about today is end behavior. So last time we talked about domain and range, and interval notation for domain and range. Today we're going to talk about end behavior, or how is the graph acting on the left end and the right end. So for instance, if you had a graph and on the left hand side of the graph it looked like this, pointing up like this and off to the distance, we would say the end behavior is as x goes to negative infinity, y goes to positive infinity. On the right hand side we would say as x goes to positive infinity, y goes to positive infinity. So as we go further and further negative for the domain, we go up for the range. So as we go to negative infinity on the domain, the range increases up to infinity. As we go up to the right, positive to positive infinity on the domain, this graph, as it goes to the far reaches of the right hand side, goes up to positive infinity as well. So it goes up on both sides. On the other hand, if you have a graph that looks like this, we say as x goes to negative infinity, y goes to negative infinity. And that negative is probably not terribly clear. It says negative right there. Y goes to negative infinity because it goes down. As x goes to positive infinity on the right-hand side, y again goes down to negative infinity. It doesn't matter what's happening in the middle. It can go up and down, it can go straight, it doesn't matter. When we talk about end behavior, of course, from the name, we're talking about the ends, the left end and the right end. Sometimes one end is acting differently than the other. So on this one, as x goes to negative infinity, as we move further and further and left on this graph, it goes down to negative infinity for the y values. As x goes to positive infinity on the right-hand side, y goes to positive infinity. And we can have the exact opposite happen, like on this one. As x goes to the negative infinity, y is going up. On the other hand, on the other side, as we move to the right, further and further, as x goes to positive infinity, y goes to the negative infinity. So when we talk about end behavior, we're asking what is the function doing as x approaches infinity and negative infinity. So as x goes to negative infinity is the left end, and as x goes to positive infinity is the right end. We have to talk about what y is doing on both of those ends. So here's an example graph, complete graph. This looks like a cubic function to me. Let's just put arrows here to indicate that it goes on forever and ever and ever. So as x goes to infinity on the right-hand side, what's going on? The function, f of x, is going up, up, up for y values. So as x goes to positive infinity, f of x is going to positive infinity. And then for this particular graph, as we move further and further left, as x goes to negative infinity, as we go further and further left, the function is going down to negative infinity. And those are the two ends. This is the right end, and this is the left end. Okay. So let's do a little bit of practice for these. Let's look at this graph. These might look familiar from last lesson. Instead of talking about domain, range, and zeros, today we're talking about end behavior. So let's start with the left end. On the left end of this graph, as we go further and further and further left, or as x goes to negative infinity, that's how we say left end, as x goes to negative infinity, what's y doing? Y is going up, so y is going to infinity. Let's do the right-hand side. The right-hand side always starts with the phrase as x goes to infinity. That's an arrow. There we go. As x goes to infinity, the right-hand side, it always starts like that. What's y doing? Well, in our particular graph here, y is going up, 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 up as we move further and further right. So y is going to positive infinity. Let's take a look at graph B. On the left end, again, we always start the left end phrase with as x goes to negative infinity. What's happening to the y values? As we move further and further left, the y values are going down, 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 down. So y is going to negative infinity at the far reaches of this function. On the right-hand side, we always start as x moves out to positive infinity off to the far reaches on the right-hand side. What is this function doing? It is climbing upward as we move outward. So up, 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 up means y is going to positive infinity. Now, C, left end, as x goes to negative infinity, that indicates we're talking about the left side. So on the left side, as we move further and further left, as x values go to negative infinity, what's happening? It's climbing up, up, up on the y-axis. So that means as x goes to negative infinity, y goes to positive infinity. Now pause for a moment. What is happening on the right-hand side of this graph? It is not going, 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 going. It is stopping right here at an x value of 4. It is not going off into the distance, into the sunset. So because this isn't going on and on and on to the far reaches of the right, we say there is no right end behavior. Okay. So that's a bit of a special case. Let's take a look at D. Left end, pause for a moment, take a look again, look what we've got here. We've got the mirror image of the last one. We've got something stopping here. So that means there is no left end behavior. It's not going off into the sunset. No left end behavior on the left. On the right-hand side, as we move further and further to the right, as x values go out to infinity, what's going on? It's going up, 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 up. So we must say y is going to positive infinity as well. All right, let's take a look at E. What's happening on the left end? Well, as x goes to negative infinity on the left-hand side, as it goes to the far reaches of the left end of the x-axis, the function is going down, down, down. So as x goes to negative infinity, y is going to negative infinity as well. On the right-hand side, this arrow is indicating we are moving to the right and down. So as x values increase to infinity, the y values are going down to negative infinity. All right, and then F, again, we have a stopping point here. So just like in D, we have a stopping point. We don't have things going off and off and off. We have no left end behavior. But on the right-hand side, we do have things going off. So let's start the phrase with as x goes to the positive infinity, because that's what right end means. Right end to the far reaches, x is the positive infinity. Y is doing what? Y is going down as we reach to the right. So y is going to negative infinity. Okay? So that is end behavior, and you must always talk about both ends when you talk about end behavior. All right. Now, another new item for today, inverses, discussing what an inverse is. When you think of inverse, when you see the word inverse, your first thought should be swap x and y. That should be your first thought. If somebody's asking me for the inverse of something, they're asking me to swap x and y values. So if someone was to give me this relation, remember what a relation was, a set of coordinates or a set of pairs. 1, 4 is your first pair. The inverse, or the swap x and y of 1, 4 is, of course, 4, 1. So that is the inverse of that point, that element within the relation. Same thing with -3, 2. Negative 3, 2 is the second element in this relation. We will swap x and y to indicate its inverse. Same thing for 7, negative 9. We swap x and y. Now let's see how this plays out on a graph. Let's graph the original relation in orange. 1, 1, 2, 3, 4 in orange. Negative 3, 2 in orange. And 7, 1, 2, 3, 4, 5, 6, 7, negative 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's go ahead and just estimate. Now orange is our original relation. Let's use a different color. Let's use blue to talk about the inverse. The inverse instead is 4, 1. 1, 2, 3, 4, 1. 2, negative 3. And negative 9, 7, so something along this area here. So the orange and the blue are inverses of each other. The orange was our original, the blue is the inverse of x and y swapped. So that's what it is visually. And since this relation is just a set of coordinated points, or coordinates, we are just getting points for our inverse. No lines, nothing connecting each other. Now, graphing inverses of functions, very, very similar process. So let's graph the original in orange. This line f of x equals 2x plus 1. We know how to do this, right? We find the y-intercept. This plus 1 is our y-intercept. And we take our slope here of 2 over 1. So up 2 over 1, up 2 over 1. If we wanted to, we could go down 2, back 1, and down 2, back 1. And we know that these points connect a line. There's nothing saying that this is only limited to a certain number of inputs. So this thing goes on and on and on and on forever through those points. Now, if we wanted to graph the inverse, something simple we could do is take each of these points and flip them on their side, right? Swap the x and y for these. So let's take each of these individually and swap the x's and y's. I'll start down here. This point right here is negative 2, negative 1, 2, 3. So negative 2, negative 3 is what this is. So the swap of that would be negative 3, negative 2. So that's the inverse of that point. This one is negative 1, negative 1. If we swap x and y, we still get negative 1, negative 1. So that actually shares a point, and that's fine, that can happen. This point is 0, 1. If I swap x and y, I now plot 1, 0. This point is 1, 3. If I swap that, I will plot 3, 1. And finally, just to keep us straight here, 2, 1, 2, 3, 4, 5. 2, 5 will be swapped for 1, 2, 3, 4, 5, 2. So the line that goes through the blue points is the inverse of the orange. Something interesting that you can visually do to check yourself that you've done the correct inverse is realize this note here. Inverses are the functions reflected across the line y equal x. Well, what the heck is the line y equal x? Let's remember what that means. Y equal x is a line, and I'll dash it in here just to show you for reference. That's a line that goes through 0, 0, because right there's a 0 for the intercept here. It goes through 0, 0 and has a slope of what? Slope of 1, 1 over 1. So the line y equal x is just up 1 over 1, up 1 over 1, right? So let's picture this line y equal x for reference sake. And you can always do this to check to see if you've done the inverse correctly. So if you take your paper or use the inside of your brain to think three-dimensionally, if you think of this original orange line, what would happen if you reflected it across our maroon dash line here, our y equal x? If you reflected this across this line, you would see, hopefully those of you who are artistically bent, you would see that this blue line is the result if you were to reflect this orange one across the maroon one. So you can always check visually, have I done this correctly? Does it look like this has been reflected across the line y equal x? Another interesting thing about inverses is the horizontal line test. So last day we talked about the vertical line test. If a function has a vertical line that goes through it more than once, it's not a function. Well, similarly, the horizontal line test tells you if the inverse is a function. So of course, if the inverse is in blue, then we would try to do a horizontal line. Is there any horizontal line that crosses this? If it crosses it more than once, then it's not a function. We're good here. No horizontal line crosses this, so it's a function. All right. So we've attacked two things so far. We've attacked end behavior of graphs graphically, as well as inverses graphically. So let me get you started on the group practice, and then I'll give you some time. We want to graph the inverses of each of these three graphs. I highly suggest you pull off points. So let's stick with our orange-blue scheme here. Orange is our original, so here's a good, nice, clean point. Here's a good, nice, clean point. Here's a good, nice, clean point, and so on. I would suggest pulling the coordinates of those points and then deciding what their inverses are, and then connecting the graph similarly to our original. So if this point here is -2, 3, what would we graph? That's right, we would graph 3, -2 as its inverse. Same thing here. If I have this as the original, -1, 0, I would graph 0, -1 as the next one. If my original was 0, -1, I would then graph -1, 0 as my next one. And it's fine that these overlap, that's fine. We just connect them. I'm going to roughly connect them as the originals were connected, as this curve. Let's keep going. We've done, let's see, have we done this one? 1, 0, 0, 1. We haven't done it yet. So there's the inverse of that orange point. And of course that will continue to curve up like this, just like the original did. And then finally, here's a good point, 2, 3. Let's flip that, swap x and y, and plot 3, 2. So that is how that's drawn. So do you see that the blue is the inverse of our original? And how do we check that visually? Well, let's go ahead and draw our y equals x line and see if visually we agree. Do you see that if we were to rotate this or reflect this original around this line, this dashed line, that this is what you would result in, the blue. So visually we can check that. So go ahead and pull points off of the next couple of graphs, and whatever those points are, swap x and y and graph the new graph. I'll give you a little bit of time. Pause the video while you do that. Alright, now that you've done that, let's go ahead and check your work. So if our original is indicated in orange, let's pull those coordinates and flip them, swap them. So let's swap the original 0, 0. Well, if you swap 0, 0, you just get 0, 0. So we share a point there. That's fine. It happens again, 1, 1. We share that as well. The next one, 4, 2, needs to be swapped for a 2, 4. And if you're like me, you're going to be running off the graph with the next one, and that's fine. You've got a point of 9, 3, and you're going to swap that to be 3, 9, and you're going to be way up here somewhere, and that's fine. Let's just estimate it to there. But we must connect these similarly and with a curve to what our original looked like. I apologize for how poorly this looks, but your curve should kind of look like this, only straighter and less hairy. And if you draw our special little friend, y equal x, you should visually see that the blue line is what would happen if you were to take the original and rotate it around this line here. So you should have a much more solid looking curve than mine looks. curling up like this. And it should be curved, it shouldn't be a line. So then I would have suggested you take this point, this point, this point, and this point as your guides and follow the same path. We'll take 1, 3 and swap x and y. So 1, 2, 3, 1 is our new one. That's the top of this. My next one would be 2, 2. So you share that, and remember there was a little bit of a curve leading between those. So you should have the same curve leading between those. Our next point that we pulled, it looks like a 1, 2, 3, 3. And so of course the swap of that is also 3, 3. And so we'll just curve around like that. And then the last point we pulled was 5, 0. So what should we do? We swap it for 0, 5 and connect that, our last point with that, with a line. So the blue indicates the inverse. Let's check visually if that makes sense. Let's draw our line down the middle here of y equal x. And yes, I look at that, I sort of turn my head or I fold my paper a little bit and I see that the blue is as if the old black one with the orange dots was rotated around this line. Okay, that's how you can check visually. Alright, so those are inverses. Inverse, swap, x, and y. Now we're going to talk about composition of functions. And our next lesson we'll talk about how to do it algebraically, but today we're just going to focus on graphically. Well, let's first take a look at how we look at these graphs just to evaluate certain inputs. So this notation here, f of -4, if we were given the algebra of what these things were, we could just plug in -4 every time we saw an x. But for graphs, if we're just pulling them off of graphs that have been given to us, what we do is we say, all right, f of -4 means I put -4 into this function. We called this function f of x. I put in -4 for an x value, and I see where that lands on my graph. So I go to 1, 2, 3, 4, and then I find where is my graph living when x is 4. My graph is living at a y value of 1. My output is 1 if my input is 4. So right off the graph, I say f of -4 is 1. Oh, my apologies. You need to slow down. Mrs. Berger, you're not going to -4, are you? No. We needed to go to -4. Sorry about that. -4 has a value of what? Of -3, yes. Sorry about that. -3. All right. So you see we input our values, and we go in the right direction on the x-axis and find where that value lives on our function. So let's do it again, but now we're looking at the g function. This is representing our g function. So we go input -2. If we input -2 into the g function, that's here on the x-axis, where does it live on the y-axis? We have to go up to here to find where it lives. And that to me looks like a 1. So g of -2 is 1. Now, g of 4. G of 4, I input 1, 2, 3, 4 into the g function, and I go find where it lives. It lives up here with a value of 1. So the y value, or the output value, is 1. And then finally, back on the f function, if I go to the f function, I go to +1. That lives up here at a y value of 2. So that's fairly straightforward, but Mrs. Berger, you were talking something about composition of functions. What does that mean? Well, watch what happens with composition of functions. Functions of functions. Lots of parentheses. Don't panic. Take one thing at a time and start on the inside. Start on the inside. So let's start in here and figure out what g of 0 is. So to start working on this monstrosity, start on the inside and find out what g of 0 is. What is g of 0. Well, 0 on the x-axis nets out a 4 on the y-axis. So now I can reduce this phrase down to f of 4. My original question was f of g of 0. When I evaluated g of 0, I found it to be 4, so I can replace g of 0 with 4. That's what composition of functions means. So now that I've replaced g of 0 with 4, I'm now being asked, well, what is f of 4? Well, that's easy enough. I go back to the f function, I go to an input of 4, and I find that it corresponds with an output of 1. Therefore, f of g of 0, or f of 4, is 1. So f of g of 0 is 1. So it's a two-stepper. You start on the inside. That's the lesson here. So let's do it again. We're taking g of f of 1. Start on the inside. First find what f of 1 is. F of 1, well gosh, we've already evaluated that. We didn't even have to look. Back up here we found f of 1 to be 2. Well, we just reconfirmed that here. So we tell ourselves, you're trying to find g of 2. F of 1 is 2, so now we're trying to find g of 2. So we go back over to the g function and find 2, and we find that g of 2 is right here. It is 1. Okay? So therefore, g of f of 1, or g of 2, is 1. Start on the inside. That's the key. Start on the inside. F of 6. No problem. We can do this. What is f of 6? We go to 6. We go down to the graph. It lives at -1. So you now are asking me f of -1. Let's go back to f. Go find -1. -1 lives here. It doesn't go up or down, so f of -1 is 0. G of 0. Start on the inside. G of 0, we have an input of 0, which means an output of what? We already figured this out. We found g of 0 to be 4. So this output of 4 means I'm taking g of 4 now. G of 0 is 4. And now I'm taking g of 4. So I go over to g of 4, and I find it to be 1. We already determined that up here, so we've just reconfirmed it. G of 4 is 1. So g of 4 is 1. So that is g of 0. So that is graphical composition of functions. All right, go ahead and attempt your independent practice.